So for section 8.3, we're going to look at two specific operations with radicals. We're going to look at multiplying and dividing. In the next section, section 8.4, we're going to look at adding and subtracting. But right now, we're just going to stick to multiplying and dividing. Let's start with dividing radicals. So let's say that I give you this particular problem. 5 root 2 divided by root 5. Now everything looks fine and dandy with this problem, but there's one issue, and that is we have a square root in the bottom. You don't ever want to end a problem with a root in the denominator. Same way you don't ever want to end a problem with a negative exponent, same way you don't ever want a zero in the bottom of a fraction. You don't want to end a problem with a root in the bottom. So you got to get rid of it. The way that you get rid of it is you actually multiply by whatever root you're trying to get rid of. In this case, the square root of 5 is what I'm trying to get rid of, so I'm going to multiply by that. Now I'm going to multiply by root 5 over root 5. Why? Well, root 5 over root 5 is 1. Anything over itself is 1. 2 over 2 is 1. 8 over 8 is 1. Root 5 over root 5 is 1. So in essence, I'm multiplying this fraction by 1. In other words, I'm not changing it, right? And that's the rule. We want to keep this equivalent. So what happens when we multiply this across? Well, root 2 and root 5, you go ahead and just multiply, so it becomes 5 root 10. And then in the bottom, root 5 times root 5 becomes root 25. Well, if you do it correctly, your denominator should be a perfect square, something you can simplify. So you end up with 5 root 10 over 5, and in this particular case, these 5's will actually cancel out, and you'll just be left with root 10, which is your answer. Okay, I want to look at a little bit more complicated problem. So what I want to look at is 27 over 16, the cube root. Let's say I ask you to simplify this. Well, at first glance, it looks simple, but I can't take 27 divided by 16. Since I can't take 27 divided by 16, what I'm going to try to do is split up that cube root. Well, this makes it a little bit easier. I know the cube root of 27. The cube root of 27 is 3. I don't know the cube root of 16. And I know from the last problem that I need to get rid of any type of root in the denominator. In this case, it's a cube root. I can't take, in the last problem we took the square root of, I think it was 5 times the square root of 5, and we were done. Square root of 25, finished. And the reason that worked was because 5 times 5 was a perfect square. We need a perfect cube to clean this out. In other words, I need to multiply the cube root of 16 times something that's going to get me a perfect cube root. If I don't have a perfect cube root over here when I'm done multiplying, it's not going to clean itself out, and I'm still going to have a root in the bottom. What was the whole point? So in other words, what I need to do is I need to go through all my perfect cubes and find one that 16 goes into, so I can make sure that I have a perfect cube. 1 times 1 times 1 is 1, 2 times 2 times 2 is 8, 3 times 3 times 3 is 27, 4 times 4 times 4 is 64. 64 piques my interest. I think 16 goes into 64. It actually does. 16 times 4 is 64. So I want you to look up here at what I've done. I knew I needed to have a perfect cube right here. I knew that I needed to take 16 times something to get me a perfect cube. I took 16 times 4 to get me the perfect cube of 64. Now if I multiply by the cube root of 4 on the bottom, I've got to multiply by the cube root of 4 on the top, giving me 3 cube root 4 over cube root 64. Now that's all fine and dandy. Cube root of 64 is going to clean itself out, giving me just a positive 4, and there's no root on the bottom, so I'm finished with this problem. Now be careful. Don't try to cancel these 4's. This guy is under a root and this guy is not. They cannot be canceled. You've got to stop right here. This is our final answer. Okay, so now let's talk about multiplying. So we talked about dividing and how to get rid of a root in the denominator. Now let's talk about multiplication. So there's actually two different ways that you're going to see this. The first way you're going to see multiplication is when you have the same index. So if you have the same index, multiplication is fairly simple. So let's say that we've got the square root of 2 times negative 3 root 5. When you're multiplying and you have the same index, in other words, square root and square root being the same index, you just take outside times outside and inside times inside. So 1 times -3 is -3. I'm getting the 1 from out here, this little silent 1. And then you take inside times inside, so root 2 times root 5 would be root 10. That would give you -3 root 10, and that would be your final answer. Now, if you don't have the same index, in other words, if you have different indices, or a different index, you might have a problem that looks similar to this. Like, for example, root 5 times the cube root of 4. And this makes things a little bit more complicated. We actually can't just multiply these straight across because one is a square root and one is a cube root. So you're going to convert it to a rational exponent, get a common denominator, convert it back, and then go from there. So let's look at this. I'm going to make this 5 to the 1/2 times 4 to the 1/3. In other words, I just converted it from a radical to a rational. Now from here I'm going to get a common denominator. The common denominator between 2 and 3 is 6, so I'm going to multiply by 2 and I'm going to multiply by 3. And I'm going to get 5 to the 3/6 times 4 to the 2/6. Okay. Now, be careful, I still can't take 5 times 4 and make that 20 because of those radicals. I can't do that. But now that I've got a common denominator, I can actually convert this back into a square root. So it actually becomes the 6th root of 5 cubed times the 6th root of 4 squared. If we clean that up even further, it's the 6th root of 125, that's what 5 cubed is, times the 6th root of 16, that's what 4 squared is. And now they have the same index. And guess what? If they have the same index, we can actually multiply across. It's the 6th root of 2000. So that is how you multiply if they do not have the same index, and you're tested both ways.